Yeah, I'm getting started. I'm Sungtek on behalf of the research group from International University. I'm going to give a talk regarding metamaterials and beamforming antennas playing the core of intelligent reflective surfaces for wireless communication, and its demo with Kahng TextWave 5G spectrum analyzer probe. So I'm going to show you the demonstration based on the experiments we have done till the end of time to prove the very bizarre effect, but actually which is exactly exists in reality. You will see how we can handle that. I'm really thankful to my research assistants, Soyejun and Jo Jung-en, and the other people. This is the agenda I'm going to have for today. Motivation will shed a light on why I had to get it started or get the kick out of this work under the name of metamaterials, reflector arrays, and IRS. And background and introduction is the next part. There you will see which works have been done in the past dealing with the improvement and enhancement of the functions for communication. Schemes and implementation will talk about the details of what reflector arrays and IRS or RIS are. And the theoretical explanation will be followed by experimental tests in the part of the validation. There you will see the students on the spot for the testing, the functionalities of the structures we have developed under the name of smart reflecting surfaces. And finally, I'll draw the conclusions. Yeah, this view graph shows you what I'm going to tell you today is a good summary of my motivation. I was motivated to improve the quality of communication, especially 5G, 6G, and beyond, because we exploit millimeter wave, which have very much limitations compared to the legacy mobile communication frequency bands. The reason is, as the frequency goes up, the electromagnetic wave tends to be very direct. So if you have some obstacles right in between the transmitter and the receiver, you will suffer from some problems, there's some drawbacks. So I would like to get over those drawbacks by having the smart materials, which you can design by yourself under the name of the reflector arrays and metamaterials, which will be evolved to RIS, reconfigurable intelligent surface, or intelligent reflecting surfaces. So here you can see the final goal is existing or located here. And this consists of the mixture of different parts. RIS, which is influenced by metamaterials, and metamaterials that should work for millimeter wave. So millimeter wave feed network and antennas are required. And last but not least, we will validate using the experimental setup. I'm going to show you, propose to you, the name TextWave we developed recently with the cooperation with the American Research Group. So you are going to see what I'm going to tell you ultimately. Here you can see some familiar pictures or unfamiliar pictures. Maybe as students or researchers from the communication society, actually this picture and all the way to the picture on your right-hand side, these pictures are quite familiar to you. Why? These pictures were sketched by the 5G or fast data transmission rate pursuers. So you can see the antenna or repeater, which is mounted on the top of the tower, and this sends the signal to the receiver here. If this frequency of interest deals with the low frequency, such as 2.4 gigahertz, such as Wi-Fi or wireless LAN, or low frequency of the 5G, it doesn't matter. But the thing is, you can see a tree that blocks the signal when we change the frequency from low frequency to high frequency. And the signal strength at the receiver side will be much damaged and disturbed by the precipitation from the clouds. So this is quite common in Ka band community. When I was working for ETRI, 한국전자통신연구원, I developed transponders and radio frequency components and antenna systems for satellites like this. Satellite these days use X band, Q band, actually KU band, and Ka band. Ka band includes millimeter wave or vice versa. So you can see the geostationary satellite, which shines the electromagnetic wave energy to the receiver antenna on the ground. But this is revamped with the new things like this. You can see a network. It's a kind of a 3D networking system implemented by we can say an army or a crowd of the LEO satellites. So this platoon of satellites are hovering over the surface, especially at the altitude of 200 kilometers up to 800 kilometers, which is way below the altitude where the geostationary satellite is located. But people started to be interested in how to link the ground mobile communication networks with the something above us, like that. Yeah, this is a kind of a new picture to you. And this picture is much related to this millimeter wave Ka band communication thing. In terms of the frequency band, they are very, very similar, or they are good neighbors in the community. And another reason why telecommunication done by satellite and telecommunication done by millimeter wave transmitter and receiver is, what is it? Line of sight problem. So blocking materials or structures should be avoided, but actually you cannot move them. So in order to, some drawbacks happening to this type of scenario, actually we are going to seek for the solution, which is RIS or IRS. That's what I'm going to address later. And this one is a familiar picture, but you can skip this. But from the standpoint of the measurement of electromagnetic wave energy, which is the front head of the 5G and 6G communication or other legacy mobile communication services, actually this measurement scheme or configuration is very important. So I'm going to set up based upon this type of approach, transmitting and receiving, and the detected strength of the received power will be read through the equipment we have developed recently. So motivation is how to avoid the shortcomings happening by the blocking structures like this. How can we avoid the problems from the blockage or shadow area? Another motivation. Actually, I'm from satellite communication side compared to mobile communication side. But these days, we handle lots of designs for antennas appropriate for mobile communication too. I have several projects working on 5G and higher frequency communication. We are interested in this type of antenna. You saw here, most of the antennas you use from the ground or from the geostationary or the LEO satellites will be reflector antenna. The side view looks like a quadratic function in mathematics or parabolic or parabola. This parabolic structure is made out of metal and is a curved structure. This is a side view of the total system. This is called the horn antenna or primary source, or just simply source. This is a reflecting surface. So horn antenna gives the 5G or Ka band signal here and hitting and bounced back to where it started and passing the horn antenna, and it reaches the receiver at the far field. This has worked quite a good job, but the thing is, it is bulky and it is really hard to maintain this. Why? The curved metal structure, if you violate the mathematical formula, such as a parabola or quadratic function, actually it doesn't work. You will miss the focal point, you will miss the target. You can see the circle from the front view and the front side view, you can see a parabola. If you do not obey the mathematical formulae, parabola and circle, actually, you cannot guarantee the right communication. So what we are going to do is to go down the prices to manufacture and maintain the system. What about changing the curved structure to a planar structure? A planar structure, it is not the curved structure. So the functions we can expect will be different. No, we should give or impose the same functionality to this planar structure. But how can be the function or the resultant function of the planar structure will be the same as the curved structure? That's what the magic, the metal surfaces can do. That's the thing I have done more than 1 decade, almost 2 decades, 20 years. So you can visit my office or you can visit my portal where a long list of the metal materials work is introduced. And let me visit the field of the reflector antenna. I was talking about the necessity of converting the curved structure to a planar structure by maintaining the same function. Reflector antennas. Yeah, you can see everywhere, almost everywhere. I took these pictures from the applications to the satellites or the ordinary mobile communication. If you go to the broadcasting stations, on top, there's a tower. You can see many reflector antennas are held there. Reflector antenna is still quite strong, but the problem is it is expensive to keep it on the right side. That's the thing. Metal materials. You should know, and it is worth knowing what metal materials or what metal materials will give you as the benefits or profits you will get. You probably have seen this programmable surface or coated surface. This coated surface has been applied to RIS or IRS. Reconfigurable. Reconfigurability comes from changing the condition or the state of the metallization. You can see the color codes here, color codes. If you refer to these references, you can find how the colors are working for you to change or to change the direction of the angle of reflection or change the number of the reflective fields. You can see that one, very high directive, and the other, and 2 beams, and 3 and 4 beams. You can polarize the beams to reflect from the hitting surface like that. But actually, don't be gullible or deceived by the kind of black magic to run this type of thing. Why? Expensive, too expensive. I should put the stress on the drawbacks or shortcomings or disadvantage, from RIS or this type of a programmable metal materials. That's why I do not spend much time in working on fully active metal surfaces. For me, I work on completely passive metal surfaces or RIS. The reason is every tile of this graded metal surface or checkerboard, can you see that? These are called the unit cells. I'm going to show you unit cells too from the examples I have made. The colors mean the states. So if you have one bit system, you have two conditions, on, off, or 180 degrees or 0-degree phase delay like that. Or you can increase the number of the bits to control the states of each of these cells. You can make it to 3 conditions or 4 conditions or 4 states. And overall, checkerboard has different pattern. That means you can change the angle of reflection, which was experienced by the electromagnetics 101 class. So you can change the angle of reflection on your own, and to your taste, you can change the number of the beams you would like to send to the air like that. But still, it is kind of daydreaming, even though a lot of people paying attention to this, and especially my friends who work on metamaterials, they kind of a hobby is to just fiddling with their metamaterials to be the RIS, but quite expensive compared to what? Legacy repeater antennas such as 중계기. Please remember that. So you should weigh the heaviness or weight of the costs from RIS development and repeater development. You should choose. But I'm going to suggest to you the very smart reflecting surfaces which get over the limitations of the classic electromagnetics. So metamaterials, actually not only the reflecting surfaces, but also transmitting or lensing surfaces too. I have had several funds from the industry, not NRF, not IITP. I got funding sources from very serious industries such as LG Innotek, LG, and Samsung Electronics, and LG Next One, etc. There I developed metamaterial lenses, very planar, but it plays the role of convex lens. You know the convex, curved structure. But it is very, very expensive to make the curved dielectric material, especially for millimeter wave regimes, such as 28 gigahertz, 38 gigahertz, 77 gigahertz, such as the car radar systems. Very expensive. So you should pick up this idea. So you can see, I could change very wide beam and low gain antenna performance to a very sharp pointy beam, very narrow beam, and high directivity. Can you see that? There's a jump. There's a jump. The scale of the jump is more than 10 dBs without using any active components. Amplifiers? No, you don't have to spend a whole lot of money for buying very expensive amplifiers or beamformer chipsets like Samsung Electronics or others do. They're rich, but actually we are not able to afford those things at the lab situations. Then you should choose this type of thing. So a number of companies are interested in my work. They keep visiting me, and I provide my solutions to them, especially repeater antenna systems. They just put very smart materials like that. Then you can change the diverging wave to you can see that almost parallel wavefront. Parallel wavefronts mean only one direction, one collaborative direction. So it is a concentration of the electromagnetic power flux. And I visit the topic reflector arrays. Actually, RIS and IRS are relatively new, but reflector arrays dated back to late 1970s or early 1980s. NASA funded some research groups to work on planar reflecting surfaces, but please be sure to have the same functions to have a beam forming. How could you do that? So I have been working on this type of thing more than almost approximately 30 years. I have seen a lot of literatures from 1990s. There was a very slow or sluggish move or development. But recently, over the last 20 years, there's a huge jump. So I am one of them. Even though the news media didn't cover me, that's fine. So you can see very planar structure, which is located or mounted on the CubeSat, small sat. This microscopic satellite cannot hold the reflector antenna, which are curved structures. Then what are our solutions? What are our alternatives? That should be planar structures. So my group has developed the very similar or the antennas of the same kind for the same purpose. Can you see that? The reflector as a curved geometry is converted to a planar structure, but it seems like a kind of array antenna, but there is no driving or feeding system underneath. And it just relies on the reflection from other source like a horn antenna or other smart primary source we have developed like that. So it is the reflectory is coined word consisting of reflector and arrays. So then hopefully from now on, you can be familiar with this term. And 5G mobile comm, I have developed beamforming and beam steering antennas. Recently, I published a paper that deals with the communication, hi-fi communication, high fidelity communication test with the beamforming and beam steering antennas I have developed recently. And you can see my paper in sensors there. My antenna can get the track of the beams from the source. Then my antenna in the receiver can pick up the, recognize the direction of, or the angle of arrival. And you can see that 64 Kahng test result, very clear, very clear. So I tested my antenna systems from the standpoint of RF and communication like that. And also my antenna, can you see that one antenna different from other groups? You can see almost 20 different angles of beam projection. It is possible. Can you see that? You can count the number of the beams or different angles, different angle along the elevation and different angle along the azimuth, so horizontal and the vertical direction. And this report just on the based on the calculation, but I did it in the physical domain. You can check my papers or the works related to my work. And RIS, finally, reconfigurable intelligent surface or intelligence reflecting surface. These two things, actually, they are the same. They are the same. They are just playing on words. When RIS, paper under the name of RIS is rejected, if you change the name from RIS to the IRS, your paper will be accepted. That's very funny. Yeah. Anyway, you can see a reflector array or the RIS system. Each of these elements or unit cell consists of this one. Can you see that? A pin diode is controlled by the DC biasing. So underneath, you have a DC biasing line, a pair of the DC biasing lines, and the control box. Then these two blocks, metallized blocks, can be connected or disconnected in accordance with the selection of switch. So you need a switch here. But what you can imagine how expensive or how power consuming from that element or from the system will be, because each of these elements should be connected to the bias lines and the control box. Oh, that's hard to imagine from the budget I have. Anyway, we would like to circumvent the obstacle or the barrier which stands in your direct link or LOS, line of sight, between the repeater antenna and the antenna of your mobile phone. So you cannot detect the received signal or from signal from the tower. So there you should detour or have a bypass like that. This building on the wall has the RIS, reconfigurable intelligence service. So as you saw, the programmable meta surface or programmable or coded surface, you can change the direction or change the number of the beams reflected from the hitting surface like that. Yeah, in my group, we are in the middle of working on lots of electromagnetic problems, including antennas or filters or many other steps. So you can see the electric field distribution animated to show you. Actually, we developed a dual band antenna system, which works for 28 gigahertz and 38 gigahertz as well, to cope with the demands from the American market. Verizon, one of the mobile carriers from the USA, they asked Samsung Electronics or repeater developers in Korea, what about dealing with the two frequencies? Because their main concern for millimeter wave communication is 38 gigahertz instead of 28 gigahertz. But 28 gigahertz, very smart choice. What, like a 120 gigahertz or 240 gigahertz under the name of 6G? I'm afraid. I'm really afraid. It is not economical at all. Even though they say deploy everywhere, repeaters and the receivers, they can get the revenue, no way. Why? As frequency goes up, you should put a lot of high power amplifiers. Actually, as users, you don't care about them, but the mobile carriers and the repeater antenna developers like Samsung Electronics will suffer from the problems, even though they do not spit it out. Oh, it's fine. But behind the scenes, lots of things, negative things happen. So 120 gigahertz and 240 gigahertz under the name of 6G or terahertz, no way. 28 gigahertz is almost the last boundary for mobile communication. You do not like to talk to people with the laser beam, right? Pointing error. If you miss the target, you cannot talk to them, right? Terahertz and 120 gigahertz or above it, the frequencies, no, it's terrible, terrible. It's a nightmare for the electromagnetic and communication people. So, I mean, even though 6G, 7G, the name or the number changes, frequency doesn't have to change. You should put other technological issues or technological development. That's my point. And people say, some electromagnetics teachers say, we increase the frequency of interest or operation, the frequency goes up. Wow, the electromagnetic wave moves faster. Never, never. The speed of the electromagnetic wave at different frequencies is the same. Same, as far as we live in the air. So the reason we have the higher data transmission from the millimeter wave compared to 2.4 gigahertz is bandwidth, just the bandwidth. Let me tell you, not right now, sooner or later, I'll tell you the urban myths, the millimeter wave people say, especially communication side, and measurement equipment providers such as, what is it? I forgot that. the Keysight and other companies, they say, hey, you should build your own anechoic chambers for millimeter wave. Don't be fooled by them. Don't be fooled by them. Why? Millimeter wave, the far field is going to increase? No, no, no. Millimeter wave wavelength is very small and shorter. How can a shorter wave to have a large or increasing radius or distance of far field? No, it's wrong. TTA or other institutes say, well, you should build your own large anechoic chamber to test your millimeter wave antennas. No way. They say, well, that's the right way, but electromagnetically, scientifically, it is wrong. So I'm going to tell you, not today. If you give me other opportunity, I will point out the problems they have. So 5G is not a black magic. It still clings to classic physics. Classic physics. I'm working for communication, but I'm working for physics too. Anyway, I was so much enthusiastic about the problem. Yeah, I should tap into the keywords and key specs. You can see several items and their related functions. Main objective for my talk and for RIS people to do is beam tilting. Especially beam tilting doesn't occur by the feeding structure. Actually, the beam tilting should be done by reflecting surface. That's the difference between the legacy repeater antenna developers and RIS pursuers or seekers. Another item is active or passive type. Mine is fully passive, but hey, you should be quite understandable about the climation. Some people say from the field of RIS or IRS, hey, my structures are passive. No, as I told you, not here, yeah. Switches are called active components that require their own driving force, like batteries, right? Active components. My filters, my antennas, without the feeds, actually they are passive, cannot generate other frequency, like mixer in the transceiver, or you cannot increase the power, like amp. Switch is a nonlinear device driven by battery, right? Because of that, active component. So I want to emphasize RIS is not passive. Operation frequency is Ka band. Ka band includes 28 gigahertz, 24 gigahertz, and the 77 gigahertz, like that. Millimeter wave. But in the millimeter wave, actually, you can go further with other names such as Q and the UV and the E and W. Have you heard of them? No. Yeah. But 77 gigahertz for anti-collision car radar systems, they also deal with the Q band and the U band and V band, the not communication, but just a sensories. And antenna gain should be larger than 10 dBi. This means by hitting the surface, actually hitting the surface can or cannot increase the directivity or the gain. But here, it's a kind of passive gain. If you concentrate the flux of the electromagnetic wave power, then you can get the gain. It is a kind of antenna gain. So you can expect that. An angle of tilting or angle of reflection. Until this time, angle of reflection was just determined by angle of incidence, right? This is a surface of reflection hitting, this is incident wave, and this is reflection, right? According to the electromagnetics, whether this is a metal surface or this is dielectric material surface or plane, such as plastic or wood, like that, reflection angle is the same as what? Angle of incidence. But in the metamaterials, without regard to the angle of incidence, we can change the angle of reflection. That's what metamaterials do. That's what I do too. So I'm going to show you, we can change the reflection, angle of reflection up to, from minus 40 degrees up to plus 40 degrees. I can increase the range of beam tilting angle, but then you will lose the directivity or kind of gain. So you should juggle between antenna gain and antenna range of antenna angle of reflection. Here, schemes and implementation. Sorry, I should drink water for a while because I'm thirsty. The people are regulated not to take off their masks except the very urgent moment like this. Schemes and implementation will tell you the theoretical aspects of the reflection and incidence of wave as well. So you will see 1, 2, 3 examples first. This is simple, perfect electric conductor, such as copper. Copper means in Korean, guri, or simply speaking, metal. So don't be confused between metal surface and meta surface. Mark Zuckerberg, he changed his company, name of the company to Meta. But before introducing Meta by him, actually metamaterial people have used that word more than 3 or 4 decades. So these days, metaverse, before people get started to using that word, we already use the word meta. Meta means artificial. So it is an artificial material. So don't have the confusion between meta surface and metal surface. Meta surface uses metal surface too. But here, this is solid PEC or metallized or metal plane, 금속판. This is a horn antenna as a primary source. You can see 1, 2, 3, 5 rays. These are called rays, looking like tentacles of an octopus. But here, the ray 1, ray 2, ray 3, ray 4, ray 5, actually they were drawn as the representation of many rays. I cannot express all the rays here. They look like fog, continuous distribution, not like these discrete forms, but just bear with me. To make things easier, especially for you to understand that, I had to just pick 5 representative rays. So here, positive angles of incidence, say for example here, angle of incidence, and on your left-hand side, these are 2 representative rays of negative angles of incidence. This is what happens in the PEC. Because the wave front or wave from the horn antenna, you know the horn antenna, right? Horn antenna, it is quite commonly seen in the reflector antenna or lots of broadcasting services. This antenna, even though it is called to have a high directivity, but it is called a ray tube. The energy is diverging. So you can expect there are many lines. These are called rays, R-A-Y-S, rays. So here, the rays are diverging, and PEC without no line or with no distortion, actually the angles of reflection are determined by electromagnetics. I told you, if you change PEC to dielectric material, plastic, wood, glass, the angles of reflection for these rays are the same. But the problem or the difference is what? The strength of reflected fields will go down. If you replace the metallized block by dielectric material, why? There are transmitting rays. So the incoming wave is going to be divided into transmitted wave and reflected wave. But I'm going to deal with the reflected wave here. But PEC, that's why I put perfect here. P, perfectly electric conductor, copper, aluminum, gold, silver, whatever, or platinum like that. Anyway, the blue horn antenna is transmitter and the red horn antenna is receiver. It can move to detect the rays, and it is what happens in the real antenna test chamber. I can analyze all the rays into, I can break this problem into these 4 pictures. You can see the final direction of the cluster of the same directed rays. Red arrow, orange arrow, green arrow, and purple arrow. You think they are headed toward the same direction, or all they are different directions, right? That's why energy is diverging, not converging. So not plane wave. Plane wave is best. Focal point is made by the converging wave, but diverging again, like that. So here, I could analyze a cluster of the rays into these. So these 4 vectors are not summed together. That's why we will lose the gain of the antenna when we have the PC. That's why people fold the flat PC to what? Parabola, like that. But parabolic antenna has lots of problems. That's why we had to come up with a metamaterial surface, which is what? Planar. So metamaterial surface or meta surface 1 and meta surface 2 have these functions. Diverging wave, people might be giving me the question, hey, professor, this and this are the same? No way. Can you see? Angles of incidence will change, right? Angles of incidence different, but angles of reflection for all the reflected fields are the same, right? The same direction. It is called the plane wave reflected field. This is what reflector antenna does. So you can do that. We could get a success in developing this and testing this. So I could break this problem into these 4 pieces of problems like this. 1, 2, 3, 4. Except the normal incidence and normal bouncing, well, it is a quite self-explanatory. I don't need to just add this to it. 교수님, 저 시간 아직 있죠? 많이 있죠? Okay, thank you. What you can see, you can see a group of rays having the same angle of incidence and different, but the same angle of incidence for another group of rays. The reflection, can you see that? Different from 4 different arrows or arrows with the different colors, but now all they are the same color and same direction. That means 1, 2, 3, 4, and this normal reflection added together, then the vectors are constructively summated. Then you can have one reflection angle. It's convergent, right? And let us explore another example. That is, not only rearrange the angles of a reflection to the same direction, at the same time, what tilting. Two functions are put into this problem. It is possible. So here, ray 1, ray 2, ray 3, ray 4, ray 5, all they have different angles of incidence, but when they are reflected, disobeying the electromagnetic wave theory, but actually this metal surface or metamaterial theories belong to electromagnetics. So I'm going to synthesize the surface of this. Some people say, I have a lot of friends who are gurus in the field of antennas and metamaterials all over the world, including me. They say it is called Huygens. You know, Huygens. Well, they call, American people tend to pronounce that, his name, Huygens, but I do not agree with that. Huygens, anyway, Huygens source. This can be a Huygens source, secondary source. So I can change all the directions of the reflected fields to the same direction. And what is more is the same direction will be tilting angle. So 1, 2, 3, 4. 4 orange arrows can be put together, or they are constructively interfering with each other. And from now on, I show you the procedural steps to synthesize. How can we design the meta surfaces? I should actually, when there was education center sponsored by KAIST, located in Seoul, I was teaching electromagnetics and filter theories and metamaterials for more than 5 years. I had my own class in the past, but there's no more MDEC, EMDEC, that is what electronics and the device and electronics and materials and device education center of KAIST, but it doesn't exist anymore. There, I spent 2 days to teach metamaterials to my students. Audiences from ADD, Samsung, LG, A3, you name it. Yeah, anyway, you should cram everything into just 1 hour and 40 minutes. So it's going to be a very tough job to you. But if you are really intrigued by my work, you should visit me someday, sometime, somewhere. Here, my target phase distribution. So the procedural step here means you should set the target phase. The reason target phase is constant here is we want to have, can you see that? The phase we accept or receive at this position for the metamaterial surface, case number 1 is we want to have the same wavefront and same wavefront. If you are confused or lost, you should see this. Yeah, this I designed a lens for LG Innotek several years back for their 5G and car radar system. You can see that antenna, the source antenna here, that the energy is diverging, but going through the planar metamaterial lens, which plays the role of convex curved structure. You can see that away from the structure, I mean approaching the far field region. This field region is a radiative near field region or Fresnel region, not Fraunhofer region, this Fresnel region. But even Fresnel region, you can see the parallel wavefronts. Parallel wavefronts means rays are the same direction. So you can see, imagine rays, the direction of rays are perpendicular to the wavefront. Wavefront and rays, like that. So please, by remembering this, we want to change the diverging wave by hitting or letting the incident waves hit the surface. When they are bounced back, they should have the same phase. That's why I set constant function for the target phase distribution. And I should, the final phase distribution I need is the metamaterial surface, the phase distribution over the metamaterial surface, as you see. To do that, we should know the second thing that is subtracted from that. What is it? This phase distribution is this one. As you see, this touches here, it travels, this ray, the electromagnetic wave as an incident wave that travels on this path travels the shortest, and this is the farthest. That's why shortest. This is a kind of a parabola function, but it is not related to parabola antenna right now, but here phase distribution is this. So if you subtract this phase distribution of incident rays from the constant target phase distribution, what you will get is the phase distribution of meta surface. So you can synthesize this. Can you see the metal strips on the FR4 or some dielectric substrate? These are the metal patterns on top of the dielectric material. There, I can, so going through this direction, you can see do, re, mi, fa, sol, la, ti, do, or like that. This direction, these phases should be implemented by the width of the strips. Can you see the difference in the width? 폭이 다르죠? 폭이 다르죠? Then you can introduce or take the beam change from when they are reflected from the surface, like that. And actually you cannot put them together when metal blocks are put them together, you know, short-circuited. Then the resonance frequency or phase delay will be totally different. So like a sampling theory, can you see that? This continuous function should be discretized like this. You ever seen like that? Yeah. But for me, I have a key to make continuous, almost continuous, but the same function of as this. But if you are interested in that, especially people from industry, to be the superstar in 5G or metamaterials or antennas, you can knock on the door of my office. Yeah, and we move on to the metamaterial surface 2. We should change the angle of reflection to a certain degree, such as 45 degrees or 41 degrees. I told you, as far as we have very finite sized structure, it is inevitable we have the ray tube. Energy is divergent. If we have ideally infinitely large structure, no diverging. I could experience even this, a little bit diffusing. You know, diffusing, 확산. Yeah, but we can minimize the effect of diffusion or divergence effect to do that. But if the industry imposes you on the kind of a restriction, hey, you cannot enlarge the structure. You should put this structure in this limit. Then you have to follow that. Yeah, that's what I do. Not like NRF, just what proposal writing kind of thing. I'm very seriously compliant with the voices from the industry. Yeah. And I'm telling you, this is a constant. This is a linearly descending function, linearly descending curve. Actually, this is not a curve. You know, this is a first order function with the negative slope, right? To tilt the beam, actually, I need to have this wavefront. I need this phase distribution here. So here, the wave travels a longer path, and here the wave travels the shorter path like that. I'm kind of a physicist to explain this to you. We already have this phase distribution of the incident rays. Why? We haven't changed the radiation source. Still, we keep the radiation source the same as before, and we subtract this new phase distribution. Phase distribution from the new target phase distribution. You finally have phase distribution of this. Then you take it. This continuous function should be sampled like this, and the bar graph is going to be synthesized in the form of the width. So can you check the differences, right? Can you the difference between these two metallized patterns? They are different, right? You agree with me? Then you will have this, tilting or inclination of the reflection wave. And you can go further. Actually, my research assistants spend a lot of time in designing the 2D. This is a 1D reflection. Actually, 1D reflector rays or RIS is quite preferable with the fan beam kind of thing. You know, fan beam? There are two types of beams, actually three types of beams: broad beam, fan beam, pencil beam. So pencil beam, to implement or to handle the pencil beam, we need two-dimensional arrays or two-dimensional structure like this. This is one-dimensional, you can change this. But two-dimensional, you can like this, using elevation plane and the azimuth plane together. So here, this is sort of the combination of these two approaches. But here, I mean, this metasurface, metamaterial surface 3 is like this. This is a plane. There's a horn antenna. We shine the light to the surface here, to the elevation angle going like this, but to the azimuth angle like this. Can you imagine what happens there? So it's highly directive, and to the azimuth side, we tilt it, but to the elevation side, we try to make a plane wave like this. So there we approach the problem or to the solution of the problem from the two dimensions, x-axis and y-axis. So you can see two curves here. One curve from the metamaterial surface 1, and the other curve comes from the metamaterial surface 2. Then you can synthesize, then this one-dimensional structure is transformed to the two-dimensional structure. You know, all rights reserved for me. So if you are filming this, but you cannot figure out how you can determine the sizes or the geometry of the unit cell, this is called the unit cell. And another very kind step to explain how we can determine the size. Actually, about the shape of the unit cell, this is metal. It is called a metallized patch. This is coated on the top surface of the dielectric substrate, whose thickness is 0.4 millimeter, and incident wave is hitting the surface and reflection. So it is unavoidable to check S11. S11 means input impedance, input port reflection coefficient. When this is designed, this unit cell is put in the plane wave setup, and you turn on the input port and giving the electromagnetic wave energy toward the surface and the reflected field. It is called S11. Some people tend to use the word gamma reflection coefficient. There, you should check gamma, no, just gamma, no, phase of gamma. So by changing the sizes, especially this is square patch, changing the size of the patch from the size of the patch 2.4 millimeter up to 30.2 something millimeters. There, you can plot the phase diagram. So patch size versus the phase there, you should get ready with this. And what I want to have this, I want this phase distribution there. I told you this distribution, phase distribution matches with the surface here. You remember that? Yeah, so unit cell number 1, unit cell number 2, and going on, and unit cell number n. So now you are sitting at the unit cell number 4, say for example, like this 1, 2, 3, 4, 5 here. I need this phase. And you compare and just draw the line to this phase diagram. It must be 60 something degrees. Then you can naturally get the proper size for that. And then you can determine the size. Can you get it? For further details, you should talk to me later. And can I drink water now? Sorry, I need a short break. Yeah, I'm really running fast. Yeah, because there's a lot of things to cover today. Yeah, but if you would like to have just pit stop or toilet break, I do not hold you there. Yeah, schemes and implementation. We are still in this part. Yeah, I told you it's kind of a controversy. The RIS people say and claim my RIS and IRS is a passive component. No. I'm telling you why this is not a passive component. And Professor, you talk about, and I will talk about this, two-dimensional metasurfaces, right? 3 different cases. All they correspond to discrete states of RIS. RIS is kind of organic thing. It can move the beam, even though it is quite costly and pricey. But anyway, I'm telling you, it's a kind of a snapshot of the RIS. So if I want to equate the RIS to reflector array I have designed for corresponding to discrete states of the RIS, you can do this. Yeah, I finally need this type of thing. But what you can put exactly the same sized patches to all the unit cells or of the checkerboard. How can we implement the small one? Or how can we implement the middle-sized one? How can we implement the largest sized one? This is the key. So you take this, or you can determine the minimum unit or block, which is called the subarray in the antenna field. You should take the subarray 2x2 or 4x4, then take it. That means what happens to that subarray or new unit cell or group is going to be replicated to the rest of the whole structure. So the rest is the history. And if we take 2x2 or 4x4 subarray, if we open the material that is backing the structure, you can see that all the switches. Can you see that? Pin diodes. So these pin diodes are driven by the chipsets. Then you can choose on, off for each of these unit cells. So say, for example, 1, 2, 3, 4, these are on. The rest of the checkerboard from the subarray are off. You can see this. And this will be the smallest one, for instance. And you want to increase the size of the metallized part. Yeah, these switches are called DC switches, not RF switches. But DC switches are also expensive if you would like to buy a bunch of them from the market. Yeah, that's why I'm focusing on the designs of the reflector arrays for discrete states of RIS. And if you want to say, yeah, like the one-dimensional metasurface, you will need this. Then you will choose 1, 2, 3. 3 by 1, 2, 3, 8. 3 by 8 patches are switched on. The other patches are not switched on, turned off, like that. So, and you can fill all the necessary space for the subarray by turning all the switches on. Then you can make the kind of a full patch. Then, according to your scenario, or according to the real-time report from the propagation modeling or propagation, then you can change the scenario, or you can switch from the one code book to another code book like that. This also occurs to the repeater development society. And this can be called a coded metasurface like that. What I already explained to you like this, the same idea. I think I'm finished with the theoretical aspects of RIS as well as metamaterials. Then I'm introducing to you the examples. The first step is to share the data obtained from the electromagnetic simulation. It is called a full simulation, which considers everything: the material property, metal, and the dielectric constant, and dielectric loss, and the truncation effect. All those things are considered together. And this is the 3D view or bird's eye view of the geometry drawn by my research assistant. And here, source antenna. We need a source antenna. And we check the far field. That means, even though, don't be confused, this 3D electromagnetic power distribution or electric field distribution is about far field. It is very far. It is very far. For 28 gigahertz, it should be larger than 50 centimeters like that, at least. But for 2.4 gigahertz or Wi-Fi, some meters or tens of meters kind of thing. Here, far field pattern is just moved to, not physically, just for a graphical analysis understanding. I mean, the geometry and the far field cannot put together, technically speaking, but for graphical understanding, in the far field zone, your antenna looks like something smaller. But here, one antenna geometry, far field, moving together. It's a kind of a graphical gesture. And this has been done, and this is being done by others and by us quite frequently. And we check the three-dimensional far field pattern. You can see horn antenna usually have a diverging wave, but after hitting the metamaterial surface, diverging wave is converging. So that's why you can see very pointy and narrow beamwidth antenna performance. And if this is watched from top like this, antenna sees this direction. But after hitting this direction will be the far field pattern. And these are three-dimensional far field pattern, and this is called a two-dimensional rectangular far field plot. So if we set this direction is theta equal to 0, theta means azimuth angular variable, theta equal to 0, 0 energy is the lowest, but to the direction of angle of 180 degrees, the highest. Can you see that? You can, these 2 points put together, they meet each other. So this is the front. Actually, this will be the front. And this, if this is, these 2 points are called, defined as a front, this will be the back. And by concentrating the E field, electromagnetic power, and tilting it to the angle of 30 degrees, it is possible. Likewise, what you can see a three-dimensional structure and the far field, especially three-dimensional far field pattern, that shows you it is being what? Deviated from this direction. And it is monitored from top, as you see. So this will be 30 degrees to here. So this is 180 degrees, 180 degrees, and you can subtract 30 degrees from the 180 degrees. This will be 150 degrees. So this is what you can expect. Good. And you can refer to the antenna gains here, 17.2 dBIs, 15.4 dBIs. Gain has increased. Good, good. So reflector antenna function is here, and also that means reflector antenna has the function to increase the gain of the source antenna. At the same time, we can tilt the beam. The two functions are satisfied here. Last but not least, 41 degrees as the angle of reflection. So source antenna hitting here, and you can see different patterns. Can you see that? Here, you can compare the metal patterns on the metal surface here. And we went further by 10 something degrees, 41 degrees from 30 degrees here. And you expect the main beam or this, the hottest spot at 139 degrees. You can get this value by subtracting 41 degrees from 180 degrees. Now, it's time to validate my method. We take very, very severe environment. What is it? I take it to here. Another of my research assistants is holding the probe we developed. Yeah, get this millimeter wave measurement equipment at $16,728 US dollars. Very cheap, very cheap. Anyway, we use our equipment to test. This is quite objectively acceptable to the industry. You can see the spectrum analyzer that shows this signal strength here. Anyway, my student is holding the probe where? Where? Outside the door. Outside the door. The reason I take this example is if we test the reflector arrays or RIS in the open side or in the wide open area, yeah, like this. This is a simple metal surface, horn antenna, shooting the EM field here, incidence, and what? Reflection can be here, ray tube. So people might be deceived by that experiment. So my scenario is this. Only I put metal surface like this. It faces the source antenna like this. Source antenna doesn't have any inclination. 기울어지지 않았어요. And metal surface, the plane of the metal surface is exactly right perpendicular to the wall. So if this metal surface is wrongly designed, the energy doesn't go this direction outside of the room. This is a door opening. Wall, can you see that wall? Wall. Wall can be what? A screen that blocks the energy. So we took this very strict and stringent environment for our test. Here, wall. So if this is a simple metal surface, actually, especially, you can expect if your metal surface is well designed, you can detect the energy farther. Close to the area, you can detect the energy, but from where? Why? There's a 3 angles: 0 degree, 12 degrees, 24 degrees. In the near field, there's a lot of noise, right? But in the far field, the target area is shown by the what? The energy. If we design or made the heating surface for the 0 degree angle of a reflection, like this, in the far field, noise is populated in the near field region, but in the far field region, I mean this. In the far field, it is quite prominent, but in the near field region, actually you can be, your experiment might be contaminated with the noise like this. So then it is hard to distinguish. This comes from where? It's a kind of environmental noise like that. To have a good angular distinction or discrimination, actually you should go many steps away from the door like this. That's why we have one distance, the second distance, and the third distance. And fourth and fifth distance can be suggested, but we had to, for the sake of simplicity, stop moving toward other farther points. But you can see the results, successful results we have made. So here again, if this is a PC or ordinary, some people just fool you or just deceive you. Hey, just a simple PC, but this is metal surface. You can use this to bend or incline your incident wave to the other direction. Just it is covered by some kind of undetachable thing here, but you cannot lie when you test it with the real RF source like this. Source can happen if this is a PEC, but if this is a metal surface, the reflected wave can escape the room. Other group developed their own RIS and tested the functionality of theirs, but actually we drive our situation to something more strict and stringent compared to this. Why? My meta surface is inside the room, but their RIS is not inside the room. What? Almost outside the room. Can you see that? You can find this in YouTube. Anyone can do. And I cast my doubt. Their source can be tilted. Then if this is well-designed or poorly designed, but you can see underneath it, it is connected with the very bulky and heavy active component circuitries. You can do this. You can receive the energy, even without being a metamaterial. So I do not like to fool or deceive other people like this. This is our test environment, and this is their test scenario. And we did it for simple PEC or metal surface and the metamaterial surface. Because there are several combinations of distance and angle. Can you see that? This is a fourth quadrant of the quadrant, cylindrical coordinates here. The origin of these coordinates is the center of the physical center of the structure, as you see here. And I give the name to this distance is, you can see the radial what distance is here, row 1, row 2, row 3. Row 1 is 94 centimeters and 141 centimeters, and row 3 finally is 188 centimeters. For the wavelength of the millimeter wave, actually, this is very, very far. For the repeaters developed by Samsung Electronics or KMW or ACE antenna, they give higher input power. For us, we use input power of 20 dBms, 10 dBs lower than that of the commercial repeaters. That's why we cannot take it to such as 50 meters or 70 meters. But if the dynamic range of this spectrum analyzer tagged along with my equipment, then we can do that. Anyway, there are combinations. We vary the distance from row 1 to row 3, and here angular variation, actually 1, 2, 3, 4, 5, 6 ticks. But here we will just representatively show you 1, 2, 3. So the angles will be 30 degrees with reference to this axis, and this is aligned with the angle of incidence, and 45 degrees and 60 degrees. Phi A, phi B, phi C. So you can take a look at these combinations here, and like radar view graph from here, you can see the moving probe or receiver. Actually, this is what I, with my coworkers, developed recently, the probe. And you can see the strength goes down when it is farther away from the surface. But you can get this lesson. What? Only the angle, because I told you the ray or the wave from the source is divergent. So PC and also diverging too. So very near the side of the wall here, you can detect the energy like this. But oh, PC has the function of the metasurface or RIS? No. Diverging function or effect. But except this, if you take further step away from the door opening, it goes down very abruptly. You can see that the level is all around minus 67 point something dBms, very small. And yeah, this is this plot is about row 1, and this is about row 2, and you can go further. So my message to you is PEC cannot let your incoming wave tilted to a certain degree, except this kind of anomaly. And we tested our reflector arrays metasurface here, and we have the same combinations of the distance and angular combinations like these. Then you can compare we will quantize these values to these curves, because what is too tiny or too small to read the measurement. But you can, at a glimpse, you can compare if you change the angle toward the target direction, because we test the 41 and up to 45 degree reflected angle of reflection by this metamaterial reflector. Like this. This area has the strongest received power compared to other angular variables. Can you see that? Here, very low. Underneath the minus 75 dBms, it is embedded by the noise floor, and this 45 degrees. So my conclusions are, get this millimeter wave measurement equipment at USD like this. Can be one of them, but I mean, don't be fooled or deceived by so-called metamaterial people or RIS people if they do not comply. Let their antennas or antenna systems comply with these kinds of experiments. And this type of approach I have shared with you all the way through my presentation, all these things. So, and that is the product of the mixture of different disciplines, subjects, and can increase the throughput of the 5G or millimeter wave communication. Thank you. And we are running out of time, but I'm letting my research assistant to show you the demo. I cannot take all of the demos I have made, but just a couple of things, just one or two. 지금 어떻게 성분 준비되어 있나?
예, 되어 있습니다.
그러면 지금 요거 내가 내리고 공유 중지하고.
핸디 말고 리플렉트부터 먼저 드리겠습니다.
준비된 거예요? 아니죠. 잠깐만요. 이게 내가 왜 안 되지? 일단. 예, 지금 공유 중지가 된 거죠? 예. 예. 그 소리는 크게 안 해도 돼. 내가 설명을 하면 되니까. 자,
in continuity of what I was talking to you, regarding the role of the meta surface, as I told you before, this meta surface is designed to tilt the angle of reflection toward 41 degrees. As the flat surface, it is almost impossible in the past, but now it is possible by us to make a change in the flat surface to have a very special function like that. So the incoming wave is hitting the surface and the reflection occurs to the surface, but with the 41 degrees of angle inclination coming. Still, probe is waiting for the receiving energy or incoming reflected energy to detect. Here.
I have two versions
So,
of
as you
probe.
remember here, this
Stationary
position,
one like this with the tripod.
the
and
probe has
help.
not changed
You can find them under the name of
angular
text
position.
wave 5G.
It keeps the 41 degrees from the previous test like this, right? But only difference we have made is the distance. The distance between the aperture of the probe to and the center of the meta surface like this. So, well, 2 times the distance we used. Now we have this probe located at farther from the surface. The reason why I had to change the position of the probe farther from the metamaterial surfaces, if you see,
This is the best angular position which is targeted by the meta surface we designed, and we will move the angular position starting from 45 degrees to upper degree angle of reflection and lower angle of reflection.
much
We will
noise,
compare them.
like side lobes. So sometimes it is hard to distinguish the its feature at the 41 degrees or the strength at a lower degree like that. But if you move the position of the probe away to the farthest point, then the noise which was around it has been eliminated and you can get the maximum strength at this position, at this angle. So we will going to check this. Let us confirm this by changing and checking the strength of the received power. Here we will read here the strength.
This spectrum analyzer is attached through the cable to the probe.
Some dBms.
You can see the green marker there that tells you the strength.
The signal strength has been lower than before. Why? At the same angular position, but the distance has increased. So it is no wonder we can see the weakening of the received power strength. But it's going to be the maximum at this same radial area. The distance is the same. This angle is going to give you the maximum signal strength. So please move this to a lower angle like this. How about this?
To a lower, sorry, one upper angle, a lower angle, but to this
As you
direction.
remember, in the previous test, a little bit of lower angle from the 41 degrees, such as 20 degrees, the signal strength was not ignorable. Why? I told you the near zone area is polluted with a lot of
We've
noise.
changed the
So it
angle
is
of
hard to
observation from
distinguish
45 degrees to
the
20 degrees.
intended
And
direction of
we expect the
reflection
decrease
and
of the signal
direction
strength of the
reflection.
received power.
Here, that's the farther point with the lower angle, but this is not the desirable angle. Desirable angle is 41 degrees here, about 20 degrees of angle. Let me check.
Let us check. Yeah, How
That
much
reads around
now?
minus 50 point something dBms. So you can see obviously the difference between the signal strength at the 41 degrees and the signal strength at the 20 degrees. So the noise has been removed. Why? We could do that by moving it further away from the surface of the material. Now we will change this probe to a higher degree of angle. Good. My research assistant has moved the position, angular position, from 41 or 45 degrees toward around, say for example, that is around 60 degrees or 70 degrees. We are wondering what happens to this probe. Let us see the signal strength. That is minus 49 or minus 50 point something dBms. So the moving the probe from the
By watching
desired
the
angle to the upper
animation
angle,
on the
actually,
spot, it's hard to read the tiny
signal strength of the
numbers
received
there.
power has
But
gone
I'm
down.
definitely telling
What we
you,
expected.
at the 45 degrees of observation, that was the best and highest in strength, around minus 40 something dBms. But other angles have, such as such as 20 degrees or 60 degrees, it will go down by 10 dBs like that, or more than 10 dBs. 그러면 지금 시간이 거의 다 됐지만 짧게 handheld 타입도 한번 볼 수 있을까?
예, 바로 드리겠습니다.
짧게 너가 스킵 해라.
Now I'm going to introduce a new probe, which is handheld. My research assistants are holding
For
this
you to
new
use
probe. Actually,
the
this
handheld
probe,
probe,
was born to
you will need the extra things such as the Steadicam fixer or holder. Then
the stationary
that might be
version.
much better for you to have just
handheld,
right answers.
version instead of being stationary. So stationary version was held by the tripod, but you can hold it with your hand. Now it is positioned at the angular position of 41 degrees. If you extend the line from the center of the metasurface to this is 41 or 45 degrees. So minus 41 dBms is right there.
Did you see a spike there?
This is hopefully the strongest point.
That means,
in the angular,
at that angular position, or in the azimuth plane, that has a certain value of strength.
더 좋아졌어요.
Yes, then a lower angle such as 20 or a kind of extremely lower angle,
near field
just
region or Fresnel region.
7
That's
degrees or
why
something.
even at a lower degree of angle for the reflection, you can get not ignorable signal strength. But what happens to the change to a higher angle? 얼마?
지금 마이너스 43 정도.
Handheld probe to the 80 degrees or 90 degrees.
It is quite compatible and have a consistent
This
result or understand analysis.
goes down.
I mean the results, the values obtained by the stationary probe and the handheld probe might be a little different because there must be some kind of offset the referencing things such as calibration, but the trend is exactly the same if you change the angular position and the distance in the cylindrical coordinates to test that. Yeah, I would like to wrap this time up. And if there are some comments or questions, 하나 받을 수 있나요? 지금
네,
시간이 되나요?
시간이 다 됐고요.
네.
짧게 질문 하나나 두 개 정도만 받으려고 합니다. 질문 있으신 분은 요 앞에 마이크가 있거든요. 요 앞에서
예, 예. 우리나라 말로 하셔도 됩니다.
마이크 안
어?
켜진
김
모양입니다.
교수님.
한번 스위치를 켜보시죠.
들리시네요.
나옵니다.
예, 예. 강 교수님 너무 발표를 잘 들었습니다. 그래서 몰랐던
감사합니다.
내용들이 많이 해결됐어요. 예. 근데 하나 그 두 가지 질문인데요. 아까처럼 그 메타머티리얼이 어떤 스티어링을 할 때 정말 광대역에서 그 넓은 광대역에서 보통 빔 스키트 문제 이런 건 없는지 하는 문제랑요. 두 번째는 보통 한번 이렇게 튕기게 됐을 경우에 한쪽으로 이렇게 모으시게 되면 올 때는 디그리 오브 프리덤이 굉장히 컸는데 혹시 우리 RIS를 통과하는 순간에 어떤 인위적으로 디그리 오브 프리덤을 조정해 버리시는 거잖아요. 이렇게요. 그랬을 경우에 실제로는 굉장히 광대역이 왔는데 실제는 두 번째 튕기는 쪽에서 디그리 오브 프리덤이 빵 죽어버리게 되면 수신 쪽에서는 하나도 디코딩이 안 되는 경우가 있거든요. 그러니까 SINR은 좋아 보일지는 모르겠지만 이게 질문입니다. 예. 그런데 실제로는 보낸 거에 비해서 실제로 풀려고 하니까는 디그리 오브 프리덤이 다 깨져 버리는 바람에 멀티 스트림이 들어왔다가 실제로 SNR은 좋아 보이는데 디그리 오브 프리덤이 줄어들면서 혹시나 다 없어지지 않을까 하는 두 번째 질문인데, 그러니까 갈 때의 디그리 오브 프리덤과 튕겨서 들어올 때의 디그리 오브 프리덤이 보장이 되는지에 대한 질문입니다.
예, 예. 우리 김동구 교수님께서 너무 점잖하게 말씀하셔서 뒤에 잘 안 들었지만 그래도 알아듣는 것 같고요. 첫 번째, 잠깐만, 제가 그래도 자료를 한번 다시 공유를 드릴게요. 예, 이제 첫 번째 질문이 이제 광대역으로 이제 빔을 넓게 잡아낼 수 있느냐 하는 것은 일단은 대역에는 분명히 리미테이션이 있습니다. 이게 리미테이션이 있어가지고 어떤 특정한 딜레이를 지점마다 딜레이를 만들려고 하면 그게 주파수 디펜던트 하거든요. 그래서 그렇게 하려고 하다 보니까 이거는 일단 협대역형입니다. 협대역형이고 밀리미터 파기 때문에 대략적으로 조금 우리가 오차가 있더라도 참아낼 수 있는 범위까지 본다고 하면 이게 막 800메가 이렇게는 안 됩니다. 우리 지금 28기가 영역에서 한 800메가 정도 해주면 딱 좋겠는데 안테나를 빔포밍 설계할 때는 한 3기가도 할 수 있어요. 저는. 그건 할 수 있지만 이 리플렉터 어레이는 보면 대략 보면은 한 500메가 밑이나 그 밑으로 밴드 리미테이션이 굉장히 심합니다. 그래서 층을 이제 많이 이제 늘려주거나 아니면 제가 여기서 보여드리는 위상을 사실 이건 스위치를 구동하기 위한 어떤 칩셋이지만 여기에 RF 이제 사실 스위치가 아니죠. 페이스 시프터까지 들어가 주면 그때는 빔을 어느 각도 예를 들어서 26.5GHz에서 26.7GHz, 26.9GHz에 같은 각도 이렇게 빔을 샤이닝하고 있어라 라고 해주면은 그거는 할 수는 있습니다. 그렇지만 이게 패시브 컴포넌트일 때는 반드시 층이 늘어나도 밴드 리밋이 심하다. 근데 그 주파수 하나나 아니면은 좁은 영역 안에서 빔을 틸팅할 때 광대역화 하는 거는 지금 근데 사실은 저는 한 90도까지밖에는 120도는 할 수 있어요. 근데 어퍼처 굉장히 커집니다. 굉장히 커져가지고 벽 전체에 붙여가지고 테스트를 해야 되는데 그게 두 번째 질문하고 관련이 있습니다. 오는 거 있죠. 우리가 보낼 때 했지만 오는 거 할 때 보면 레이 튜브 때문에 이 플럭스 다 퍼져 있잖아요. 그죠? 그럼 벽 하나를 다 써야 될지도 모릅니다. 그래서 얼라인먼트가 정확하게 맞아도 없는 것보다는 낫지만 그래도 그게 대부분 에너지 이걸 모아주는 게 없으면은 그래서 저는 창에다가 투명한 메타머티리얼 렌스 지금 만들고 있거든요. 그런데 그게 일단 벽은 벽이고 창은 창이라 가지고 한계는 다 존재하고 있습니다. 그래서 이거는 좀 인도에서 이제 어느 정도 정해진 시나리오 안에서 쓰는 것으로 보고 있고요. 저는 위성 쪽에 이제 반사판 안테나 대체하는 쪽에 특히 많이 적용하고 있습니다. 픽스트라 가지고. 교수님 질문 감사합니다. 제가 또 더 말씀드리고 싶으면 시간이 이제 다른 분들 쓰셔야 될 것 같아가지고. 그죠?
네, 재밌는 내용이 너무 많은데 시간이 좀
예, 예.
제한이 있어서요. 네, 쉬는 시간 이용해서 또 추가적인 질문 해주시면 좋을 것 같고요. 다시 한번 열정적으로 강의해 주신 강승택 교수님께 큰 박수 부탁드리겠습니다.
자, 수고하셨습니다.
네, 튜토리얼은 두 번째로 이제 넘어갈 거고요. 5분 있다가 50분부터 시작하도록 하겠습니다. 잠시 휴식 기간을 갖겠습니다.